All right, what's up, guys? We got the last video in this series coming up. We just got kind of one thing that I left out of the last one. I know the last one was kind of long, so we're going to make this one super short. We got one thing that we didn't talk about. So this thing called precession. So about 2,000 years ago, Hipparchus compared the positions of certain stars to their positions 2 centuries previously. He had data on this and like where they were at. He discovered that the celestial poles in the equator are slowly shifting positions across the sky, and this is due to the precession, something called precession of the Earth. All right, the best way to think about this is to imagine, as you can see in the picture on the slide, the Earth as a spinning top. So it kind of wobbles a little bit. If you've ever messed with a top, you know that it spins very quickly, but it still kind of wobbles no matter how fast it spins, and that's kind of what's going on here. The axis of rotation is not stable. It's not perfectly balanced and all that. And despite what you might think about, the Earth and celestial objects, the Earth isn't perfectly balanced either. The axis of rotation sweeps out a circle like a cone, so it kind of with the tip tracing the circumference of the circle, and the top is what we call it precesses, meaning it kind of wobbles around and moves as it spins. This happens with the Earth as well, believe it or not. The Earth's rotational axis is kind of tipped at a 23.4 degrees, as you can see right up there. Let's get the laser pointer here. Yeah, so 23.4 degrees from vertical. The Earth has a slight bulge around its middle due to the gravity of the sun and the moon pulling on that bulge or that middle. It causes this axis of rotation to twist upright relative to its orbit, meaning it kind of wants to come back and stand upright. All right, but it's tilted at this angle. So combine that with the spin of the Earth, this rotation that happens once every 24 hours, it causes this precession. At the moment, its axis of precession points near or almost directly at Polaris, the North Star. There was a question asked in class about if other planets have other stars other than the North Star, Polaris. And that's absolutely true. They do. All planets have a different North Star. They don't all point directly to one point in the sky. It's wherever their celestial pole north points, that's where their North Star would be. And matter of fact, our North Star won't always be Polaris. Check this out. The North Celestial Pole currently points at Polaris, and Polaris is, oh my gosh, I'm going to find it here. There it is, right down there. And we're moving this way. All right, we're moving around here. So at somewhere around 3000 BC, to right now 2020 years AD or CE, excuse me. So BCE, AD, BC was the old version. Anyway, our current time 2000. So in 5,000 years we've made this much precession. All right. So in another little while, like Vega's over here, at 14,000 years we'll be over there. So it's a very large circle. All right, and it also takes a very long time to precess around that. It's not like a top. It doesn't wobble like this. It's something that you probably won't even notice if it was a top standing in front of you because it takes so long. It traces out this circle shown. It takes 26,000 years to complete a full cycle. So right now we are actually just on the other side of Polaris. All right, and so we're going to be moving away from Polaris over the next several thousand years. This is not something that you're going to notice. You just need to know that it exists. And in the history of the universe and the history of our Earth, that's a very important thing. It precessing around and changing the orientation changes its orientation on the axis that it spins or rotates around the sun. There's kind of some impacts to this that we'll get to later that have to do with with climate change. So not only if this precession thing, along with a couple of other things, all happened at the same time, this is where they believe that we get things like the mini ice age that has popped up before. So kind of just that's just the one thing that we forgot to talk about in the last video. I got a lot carried away last time, but we'll do a summary real quick of the whole chapter right now. So the sky is divided into 88 constellations, modern boundaries defined by the International Astronomical Union. Most of them are Middle Eastern and Greek mythology related. Their names are in Latin. Groups of stars that are not constellations but smaller groups like the For instance, the Big Dipper is an asterism, and it's part of the constellation Ursa Major. The names of the stars usually come from ancient Arabic. We refer to them now modernly as the constellation and a Greek letter which coordinates to its brightness, Alpha Centauri, for example. Astronomers refer to the brightness of stars using a magnitude scale. First magnitude stars are bright, second, third, fourth, and so on. The apparent visual magnitude is what you look at when you see the star in the sky. It's only the light that's coming, that's visible light that the humans can see from Earth. All right, flux is a different measurement. It's the amount of light energy that hits a square meter per second. All right, and this is a good definition, or a rigorous definition, they would say, of measuring light energy received to the Earth. We talked about the celestial sphere after that being our scientific model for how the entire kind of space, viewing of space is for us. It's kind of how the stars appear to be attached to this sphere. All right, or holes poked in a sphere. We talked about that a little bit. The falling behind point on this is that it doesn't tell us the distance to the star. It assumes that everything's kind of on one level, which is really how we observe it anyway. North and south celestial poles are the pivots in the sky. They rotate around the horizon. That's defined by north, south, east, and west. Straight up ahead is zenith. The point directly underneath your feet is the nadir. Celestial equator, we talked about that. That's dividing the hemispheres. It's just like the hemispheres of Earth. It's just an extension of the equator of the Earth into the sky. The sky distances to things in the sky are angular measurements, angular distances, arc minutes, degrees, arc seconds, and they're not really true distances between the objects. The true distances we measure in light years, but the angular distance is our observational look. We look and observe something that is 2 degrees apart, or like the size of planets. The size of the moon and the sun are both a half a degree in diameter. And so those are kind of, if you know anything about polar coordinates and the math related to that, or even about on the Earth, like our geological GPS coordinates are all measured from the center of the Earth, and we're on a sphere. So it's the same kind of idea to measure distances along a sphere. Much what you see depends on where you're at. Southern hemisphere is not visible from northern latitudes. To see that part of the sky, you've got to travel over the Earth's surface to the equator, or below the equator to the southern hemisphere. Circumpolar constellations, those are ones that are close enough to the pole that they do not go down below the horizon, and therefore they don't rise above the horizon either. They kind of circle around in the sky. We've got a couple of those. The Little Dipper and the Big Dipper are both circumpolar, north circumpolar constellations, and they're fairly common for us. Lots of people have seen them. Lots of people have located those two asterisms in the sky. And if you think about it, if you lived in the southern hemisphere, in parts of like southern Africa, Australia, southern South America, and Chile, or Argentina, you would be in the southern hemisphere and you wouldn't ever see the Big Dipper or the Little Dipper. So what we think is kind of common for the north is not something you see in the southern hemisphere. The angular distance from horizon to the North Pole always equals your latitude. So for celestial navigation, it's kind of the same thing in a way, because they're both measured from either the Earth out or from the center of the Earth. Anyway, and then finally today we talked about precession, and we went through enough of that in this video. We don't need to review it. There's the slide if you want to pause and write that up. So hopefully this video wasn't very long, and we will see you guys next time. Thanks.